Acids, bases, and the pH scale. Acids were first recognized as a class of substances that tasted sour. Vinegar tastes sour because it is a dilute solution of acetic acid. This hydrogen is responsible for acetic acid's acidity. Many fruits are sour because they contain citric acid. The hydrogen atoms shown in red are responsible for citric acid's acidity. Bases, also called alkalis, are characterized by their slippery feel. An example of a base is sodium hydroxide, NaOH. In contrast to acids, many bases contain hydroxide groups. An everyday example of a base is Drano. This is a concentrated solution of NaOH and is used to unclog drains. Extreme caution should be used when using Drano because it is a concentrated base. In 1884, Swedish scientist Svante Arrhenius was doing experimental work with electrolytes. These are substances, liquids or solids, that can dissociate into ions when dissolved in water. He was the first person to explain the essential nature of acids and bases. He postulated that his experiments could be explained by these ideas. Acids produce H+ ions in aqueous solutions, and bases produce OH- ions in aqueous solutions. His postulates are used in this course. You don't need to remember his name. Note, an aqueous solution, abbreviated as AQ, is formed when something is dissolved in water. An acid contains a hydrogen atom and dissolves in water to form a hydrogen ion, H+. So here we have HCl becomes H+ plus Cl-. Hydrogen chloride gas is an acid because it creates H+ ions when it dissolves in water. H+ is the cation it forms, while Cl- is the anion. Note that the states of the reactants and products are given in this chemical reaction, with G indicating it is a gas and AQ indicating it is aqueous, dissolved in water. A base contains hydroxide groups and dissolves in water to form OH-. Solid sodium hydroxide, NaOH, is a base since it dissolves in water to form OH- ions. Na+ is the cation it forms, while OH- is the anion. Note that the S indicates that the NaOH is solid. When Arrhenius proposed his definitions of acids and bases in 1884, it was a major breakthrough. It remains intuitive and adequate for our work in this course, though it has been supplanted by two later theories. One later discovery was that the H+ ion does not exist in water. Instead, it reacts with a water molecule to form the hydronium ion H3O+. H+ plus H2O becomes H3O+. This course continues to refer to H+ rather than H3O+, though the latter is what is actually present in water. We will use H+ and H3O+ interchangeably. pH is defined as the negative base 10 logarithm of the hydronium concentration when concentration is expressed in moles per liter. Do not use the units in the equation. When calculating pH, keep the same number of places after the decimal as there are significant figures in the concentration. The pH scale ranges from 0, very acidic, to 14, very basic, for most solutions. It is based on the highest hydronium ion concentration being 1m, and the lowest hydronium ion concentration equaling 1 × 10⁻14th m. A neutral solution is represented by a hydronium ion concentration of 1 × 10⁻7 m. Using the pH formula results in these pH values. An acidic solution would have a pH of 0, a neutral solution would have a pH of 7, and a basic solution has a pH of 14. Distilled water is neutral, so it has a pH of 7. Solutions with a pH above 7 are considered basic, and solutions with a pH below 7 are considered acidic. The greater the hydronium ion concentration H3O+, the smaller the pH. The scale shows that the difference of 1 pH unit is a factor of 10 change in hydronium ion concentration. A difference of 2 pH units is a factor of 100 change in hydronium ion concentration. A difference of 3 pH units is a factor of 1,000 change in hydronium ion concentration, and so on. For the most accurate pH measurements, we use a pH meter. The meter measures the difference in voltage between the solution and the solution in the probe. The instrument then converts this to a pH reading. All pH meters must be calibrated against solutions of known pH before use. For less accurate measurements, litmus paper can be used. Red paper turns blue above a pH level of 8. Blue paper turns red below a pH level of 5. These papers are usually a combination of different organic dyes that change color over different pH ranges.